for, again, hybrid systems falsification. And the presenter here is Zhenya Zhang.
Yes.
The floor is yours. Can you make it full
Thanks.
screen?
Can you see my screen?
Yeah, now it's good.
Yeah, thank you very much for the introduction. Hello, everyone. This is Zhenya Zhang from Nanyang Technological University. So this work was done when I was in National Institute of Informatics, jointly with Paulo. And in this talk, I will introduce a Gaussian process-based confidence estimation method for hybrid system falsification. So let me firstly give some background. So self-critical systems are everywhere in our life. So due to the existence of both continuous and discrete dynamics, they're also called hybrid systems. They are expensive and electrical. So unexpected behaviors of self-critical systems can cause catastrophic consequences. So quality assurance problem is quite important. So verification and falsification are two basic quality assurance methods. So verification is based on system state exploration. However, due to the continuous dynamics of CPS and their system complexity, verification usually suffers from the scalability issue. In contrast, falsification searches for a counterexample that refutes the specification. It's goal-guided and usually employs some intelligent search algorithms. So compared to verification, it's more feasible. Actually, falsification has been adopted, widely adopted in industry and academia. So formally, falsification is defined like this. So falsification considers a black box model M, which accepts an input signal U and gives output signal MU. User can predefine a specification in temporal logics, and the goal of falsification is to find the input signal U such that corresponding output signal MU violates the specification. This is an example of this black box model M, which is an automotive system that accepts input signals such as throttle and brake and gives output signals such as speed and RPM. They usually use the signal temporal logic, and this is an example of the signal temporal logic. It says that always within this time bound, the speed is below 120. And falsification is based on the semantics of signal temporal logic. And let me use this simple example to illustrate what it is. So here, let's consider this simple example. And suppose we have three different signals about speed and time. We can see that the first two signals satisfy this property, while the last one violates this property. And actually, that is the Boolean satisfaction of these signals to the property, true, true, and false. The quantitative robustness gives us three real values that are the distance between the largest point of each signal and the threshold 120. It basically says that although both of the first two signals satisfy this property, the first one satisfies this property more robustly than the second one. The last one gives us a negative number, and it already violates this property. So in this way, it transforms a Boolean value into a real number. And based on that, falsification can be transformed into an optimization problem. It takes this robustness as the objective function and then searches in the input space. Try to minimize this robustness as much as possible. Once a negative robustness is observed, then we are done. So to achieve that, we usually use the so-called hill climbing optimization algorithms. Let me illustrate what it is. So basically, it takes a random sample, and then it takes the next random sample. And then based on the observation of the value of the robustness of these two samples, it decides the direct direction to take the next sample. We can see that compared to random sampling, this method is more intelligent. And actually, there have been a lot of mature tools such as Bridge and S-Stereo that implement different kinds of hill climbing optimization algorithms. So in this work, we will consider a different problem that is a confidence estimation for falsification. Let's firstly take a look at a conversation between a user and an engineer. So the user asks that, is my system safe? The engineer answers yes, because I used falsification that run 5,000 simulations with different inputs, but no safety violation is found. Then the user asks, is it possible that the violation still exists? The engineer answers, yes, it's possible. And then the user asks, how likely does that happen? Then it's hard to answer. Indeed, this is an intrinsic problem of testing. So when there's no counterexample found, it doesn't give you any safety guarantee on the safety of the systems. So in this work, we propose a confidence estimation method based on the simulations run by the falsification. So formally, the confidence estimation problem is defined like this. We are given a finite set of pairs. Each pair has an input signal U and the corresponding robustness RU. And it requires a confidence C normalized in this interval 0 to 1 that indicates the likelihood that there exists no input signal in the input space such as corresponding robustness is negative. So let me overview the approach. So basically, our approach treats the falsification sampling history, that is called the falsification data, as a training set. And then we use the Gaussian process regression to train a Gaussian process that approximates the relation from the input signal to its corresponding robustness. The advantage of using Gaussian process is that for any unknown input signal, it infers a Gaussian distribution that naturally contains the information of how likely this point is negative. And based on that, we sample in these suspected points. By definition, they form a multivariate distribution. And then we do a cumulative probability calculation and then we take that value as the confidence. And then let me go into the details of the approach. Let me first introduce why we select Gaussian process as a surrogate model for the relation from the input signal to the robustness. So Gaussian distribution is something we are very familiar with. Gaussian distribution is identified by a mean and a covariance matrix. And a Gaussian process is an extension of Gaussian distribution to the continuous domain. And a Gaussian process is identified by a mean function M and a covariance function K, which is also known as a kernel. So this covariance function takes two inputs and returns the correlation between them. So in a Gaussian process, the closer two points are, the higher correlation they have. That basically also applies to cyberphysical systems. So in cyberphysical systems, 2 points that are closer in the input space will also have the closer output values because of the continuity of the dynamics of cyberphysical system. So basically, it's valid to select Gaussian process as a surrogate of cyberphysical systems. And then we want to train a Gaussian process using the JP regression. So this is a very classic method. So initially we have a JP pair, which is identified by M0 and K0. So as a convention, this M0 can be just selected. M0 can select a constant as its value. So we can select 0. And then this kernel has some function templates. In this work, we select one of the most commonly used kernel that is called squared exponential kernel, which is parameterized by 2 parameters, that is theta f and theta l. So the initial value of theta f and theta l just identifies this K0. Then the training consists in searching for the optimal value for theta f and theta l such that they maximize the likelihood of the occurrence of the training set under theta f, theta l. This can be done by some numerical method. And by fixing theta f and theta l, we got our Gaussian posterior. So based on this Gaussian process posterior, we can do inference for any unknown input u, which follows a Gaussian distribution. And its mean is calculated in this way, and its variance is calculated in this way. This is based on the Bayes theorem. Okay, so far, we already have a Gaussian process that approximates the relation between the input to its corresponding robustness. And then we want to answer a question that what is the probability that there exists no point in this Gaussian process whose robustness is negative. In general, this question is hard to answer. It's hard to give an exact answer. Here instead of an exact answer, we use a sampling-based method to give an approximation. So for example, if we take a look at this figure, so suppose we have this Gaussian process. Oh, sorry. Suppose we have this Gaussian process. So we want to sample these green points that as a representative of this area, and then to calculate the probability that none of these points are negative. Note that such possible points are infinitely many, but to give an approximation, it suffices to sample a finite number of set of these points. So our goal here is to find the representative points that are likely to be negative, and then we calculate the cumulative probability that none of the points are negative. So we do a so-called minimization sampling algorithm in which we take the 95% lower confidence bound, that is this line in this figure, as the objective function. We do a global search by random sampling in this input space omega, and then we sort those samplings singly according to their lower confidence bound, and then we take the first H points. Then for each of the points, we do a local search to find the local optima. So we got a finite number of samplings in this area. These points, by definition of Gaussian process, they form a multivariate Gaussian distribution. And then we want to calculate the probability that none of these points are negative. That can be done by using the MVNCDF, that is a multivariate normal cumulative density function. And a state-of-the-art method is given in this paper. We use that. And let me go to the experimental evaluation. In our evaluation, since it's hard to evaluate our measure because there's no ground truth, so we evaluate our method in a metamorphic fashion. For example, in RQ1, we evaluate the monotonicity of our measure, that is, as the number of falsification samplings increase, if we would expect a higher confidence to be achieved. And in RQ2, we evaluate the soundness of our approach, that is, the harder problem is, the higher the confidence to be achieved. And in RQ3, we evaluate the confidence of some existing falsification algorithms. As benchmarks, we select 3 symbolic models, that is from the falsification community, that is automatic transmission, abstract field control, and free-floating robot. As specifications, they are listed in this table. And for RQ3, we select 3 falsification algorithms, that's random, semi-AES, and MCTS. So let me firstly introduce RQ1, in which we want to evaluate as the number of simulations increase, if the confidence will also increase. That the confidence is indicated by this blue line. So as we observe in these examples, in most cases, it has this tendency to increase monotonically. However, it's not always true. For example, like this one, and also in some part of this figure, so it can decrease sometimes. We analyze the reason, and we found that since Gaussian process regression is kind of prediction for the unknown points. So once it give a wrong prediction, which is refuted by the future samplings, then it can decrease. But in general, it has this tendency to increase monotonically. In RQ2, we want to evaluate the soundness of our algorithm. So here, what we do is that for each example, we evaluate on the same specification with different parameters, and then we use this minimum robustness as the indicator of the difficulty of the problem. What we expect is that as the minimum robustness increases, we also want this confidence increase. Like in this example, as the minimum robustness increase, it indicates the problem becomes harder. So we also want this confidence increase. Okay, so by observing these results, we conclude that in general, this is also true, but there are also some counterexamples that is due to maybe like the samplings and some other factors. In the last RQ, we want to evaluate the confidence of existing falsification method. Here we evaluate random, which is pure exploration, CMES, which is a pure exploitation, and also MCTS, which is a balance between exploration and exploitation. Basically, we conclude that our confidence measure favors the falsification algorithms that provides more exploration, because you can say the confidence of MCTS and random are really high. And MCTS can, which is a balance between exploration and exploitation, can achieve a high confidence level. So let me conclude this work. So in this work, we propose a JP-based confidence estimation measure that measures how likely the system is not falsifiable in the absence of counterexample. We evaluate the monotonicity and the soundness of the proposed confidence measure, and we assess the confidence of 3 existing falsification methods. As future work, firstly, we want to investigate the influence of kernel selection, because as I mentioned, the prediction precision is quite important, and kernel selection is quite important for JP regression. We also want to devise a method to mitigate some known problems in falsification, such as the scale problem. Yes. So that's my talk. Thank you very much for your attention.
Thanks very much for the talk.
Thanks.
We've got time for some questions again. Can you please either raise hand or post a question in the chat or Q&A rubric? Yes, there is another question by Andre, I think. Is that correct?
Mm-hmm. That's right. It's not a leftover virtual hand,
yeah, sure.
although you never know. Right.
I lowered your hand, actually.
Yeah, excellent. Thank you, because I checked later on and whoever I had actually done that. Thank you for your help. Yes, indeed. Very nice talk. I do have a question. Have you ever considered trying out what happens on like adversarially annoying bad examples? I mean, the usual suspects would be traces that are mostly flat and then have thin huge spikes or so, because they should be breaking all the assumptions that are needed for being able to get a correct estimate.
Yeah, I'm not sure if I understood correctly, but
all right,
here, this assumption is important.
Yes.
So yeah, I think this method works when when the system kind of satisfies this assumption that is kind of continuous, the system. So 2 points that are closer in the space will have closer output values. Yes.
Okay, let me clarify. This is an important assumption that you're making here, and of course, a system that switches or reaches a decision would break the closeness assumption, but that's not what I was worried about. I'm wondering, there must be another assumption somewhere, and I'm trying to see where that is in your approach. Because if you have a system that has a huge derivative, or lots of spikes somewhere, it's mostly flat. Imagine a trace that's mostly flat, and then every once in a while it has a gigantic spike. These are very hard to detect by any sampling-based techniques. And in fact, you can prove that they're impossible to detect by any sampling-based techniques. I'm wondering, where in your approach do you make an assumption that the system is not like that? And have you tried what happens with the falsification techniques if you run it on a system that is like that?
Okay, I think, yeah, that's actually a good question, and also one of the future work I used to consider, because I think now the benchmarks I selected are very continuous. And I think maybe in the case you mentioned, we can use a kind of combined method, maybe but of course it needs some domain expertise. That's my guess. But yes, I think the current method cannot really handle that problem.
All right, thanks.
Yeah, thank you very much.
Right. Is there another short question, perhaps? Maybe a very short from me. So how would you try to approach the problem of scale that you also mentioned in your future work?
You mean the scale problem, right?
Yes, exactly.
So currently, I think the scale problem is because that's so in the semantics of the signal temporal logic, it compares the signal values from no, the robustness values from different signals. So that has a scale problem. However, it doesn't break this continuity of this of the robustness function.
No.
So somehow it still works well. However, I believe this still can cause some problem. Yes. Like in the benchmark, I don't see a very big influence of that,
Okay.
but you say like 84, it doesn't perform very ideally. Maybe that's the problem. Yes.
Okay. Well, thank you. I think we have to really leave it here because we have this time pressure. Thanks very much for the interesting talk.